variable. And our alternative hypothesis is that there is a relationship between our dependent variable and independent variable. Now, when you will do the regression analysis using SPSS, you will see that with every beta I, we will have a p-value, and that is the p-value that we discussed in our last lecture when we were discussing the hypothesis test or the t-test. If the p-value is less than the assumed significance level, and which in most of the case is 0.05. So if the p-value is less than 0.05, if your significance level is 0.05, if it's 0.1, then the alpha will be 1. So if the p-value for a beta or for a dependent variable is less than 0.5, then our hypothesis that it's not influencing the independent variable is not influencing the dependent variable is rejected. So when you see that your p-value for a beta or for a regression coefficient is less than your significance level, or let's say it's less than 0.05, then your null hypothesis that your independent variable is not influencing the dependent variable is rejected. Or alternatively, I should say that your independent variable is explaining the variation in your dependent variable. So if it's less than 0.05, then we will keep it. If it's greater than 0.05, then we discard that variable, because although it's in the model, but that independent variable is not explaining any variation in our dependent variable, or there is no relationship between the dependent variable and an independent variable. We just added it there. So we should better take it out, because if it's there, then a person who knows statistics or who knows the regression model well, he or she will point out that these independent variables are not explaining anything. So why do we have them? So that t-test, or those p-values for beta I, tells you whether a particular independent variable has some relationship with your dependent variable or it does not. That is the one test. That is the first test. Then as we said that for a regression model we have set of assumptions. So how do we check those assumptions? The first assumption is that the constant variance, which means the distance of the variance from its mean is constant for all the errors. Now, how do we do that? How do we check that? The first check is that we plot the residuals against the fitted values. Now, what are the fitted values? The fitted values are the values of y that you determine using your model. So you had dependent variable, you had a dependent variable, you have a set of independent variables, you conducted regression analysis, and then you got a model which says that y is equal to beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. That is your regression model. Now, using that regression model for each value of x1, x2, x3, you determine a value of y. That value of y is your estimated value of y, or that is the fitted value. So when we plot the residuals, and residual is something which is the difference between the fitted value or the predicted value and the actual observed value that you collected in the field. If when we plot the residuals versus the fitted value, then we should not see a pattern here. Like for example, in here, we don't see any pattern. It's not going in any particular direction. They are all scattered all over the place, which means that our assumption that the errors have a constant variance is fulfilled, is satisfied, is validated. So that's the first assumption that you have checked, which is the errors have constant variance. When you plot the residuals against the fitted values, then you should get a random scatter. There should not be any pattern. However, if it's showing you any pattern, for example, if it's smaller here and then all these points are being scattered like a fan, like they are going this way and then they are going this way, which means it's showing you some pattern. The variance of the constant, the variance of the errors is not constant in that case, because it's showing you some model. Or if it's going in this direction, you have a fan scattered layer. You have all scattered points over here, and then they are merging at one point somewhere here. Again, it's showing you some kind of a pattern. Then your assumption is not satisfied, which means your model is not correct. You should go and do some maybe take out some points, take out maybe whatever else you need to do that, and then conduct your analysis again. Now here, this is an example that I found somewhere. You see kind of a pattern here. All these are the, again, residuals. They are plotted against the predicted values of y, and you see that all these are randomly scattered here. However, they are confined here at one point. They are kind of merging at one point. So this kind of shows a pattern that all this is scattered and then it's merging like this. So anything that's showing you a pattern, if this scatter plot is not randomly scattered but is showing you some kind of a pattern, then it means that your assumption that the errors that are coming out of a regression model have constant variance is not satisfied. If that assumption is not satisfied, then you go back, make some changes, maybe do transformation, or recode your values or something so that your assumption is satisfied. All these tests are very important. So it's not just that you go and then you develop a regression model and then you start using it. It's not that. You have to make sure that the model that you have developed makes sense, because that model, maybe somebody else will use that model. And why the models are important? Well, the reason why we develop the models, so that knowing the past, we can predict the future. So if something based on the past, you haven't developed something which has a value, something which is reliable, then whatever decision that you will make based on that model will not be a good decision. Then our second assumption, that the errors that have come from the model, these are normally distributed. And how do we check that? The one way of checking is that we do a QQ plot, and we have that facility in SPSS to do a QQ plot. When we do a QQ plot, then the assumption is that, okay, let me take this out from equation 6.5 is not here. Okay, so when we do the QQ plot, then all these errors, all these blue dots are errors that have come out from the model. They should be plotted on a straight line. You see this, all these errors, they are close to this straight line, or they are following a straight line. If when you do this QQ plot, the QQ plot actually is the plot of the normality, is to check the normality of the errors. When you do this plot, then you see that all your errors are following a straight line. So for example, in case over here, see, these errors are not falling exactly on this straight line, but they are deviated, which means these are maybe due to some outliers. So if it's very significant, or if you plot your errors and they are something like this, then which means they are not close to this diagonal straight line, and then again you go back, you make changes, like you may try to clean your data, do the transformation, whatever you could do to improve your model. So this was the second check. Now the third check. So before we do this check, let me explain what the multi-collinearity is. Sometimes, as we saw in our first slide, or in our second slide, that the posted speed and the segment length were also correlated with each other, which means then the two independent variables are related with each other. In your regression model, make sure that your independent variables are not related with each other. They are independent of each other. And the reason Why this is so? Because when we interpret this regression model, we say that when I keep x2 constant, x3 constant, when I'm not making any changes into x2 and x3, and if I make a unit change in x1, then how much y will change? That is how we interpret this model. But and then or if I when I keep x1 constant, x3 constant, and I make a unit change in x2, how much y is changing, or how much y will change? So whenever we make a unit change in either x1, x2, or x3, we are keeping all other independent variables constant. However, in case of multicollinearity, that is when your x1 and x2 are correlated with each other. So when you change x1, your x2 will change as well. And you won't know that which of these independent variable is explaining the variation in y. So our third assumption is that, or the third check that we do whenever we develop a regression model, is that there should not be a multicollinearity, or the independent variables should be independent of each other. They should not have relationships with each other, or they should not vary. When we make change in one independent variable, the other independent variable is not being affected. It remains constant. So that is we call checking for multicollinearity. Now, to detect collinearity between variables, what do we do? How does SPSS do that? There is a method in that. What it does is, it takes one independent variable and develops a regression model using others. So it's like the same, like when we have a dependent variable and then we develop a regression model using our independent variables. To check the multicollinearity, what it does is that for each independent variable, it develops a regression model. So considering, for example, our postage speed is an independent variable. So to check for the multicollinearity, what it will do is, it will take postage speed as a dependent variable and all other independent variables as independent variables. So and then it computes the value of r square. So for example, in that case, if I take postage speed as a dependent variable and I develop a regression model using other variables such as segment length, such as excess density as the independent variables, and if the value of r square is high, that gives me a click. That tells me to see the postage speed, which we were considering as an independent variable, itself is dependent on other independent variables. There is a relationship of this independent variable with other independent variables, which means there is a multicollinearity. So it develops for each predictor j is regressed against all other predictor variables, and a coefficient of determination rj square is computed. Then 1 minus rj square is called tolerance, and the inverse of tolerance is called variance inflation factor, or in your SPSS output you will see it is as VIF. So once it compute rj square for each independent variable, it computes tolerance and it computes VIF, or variance inflation factor, which is the inverse of the tolerance. So the closer the value of VIF to 1, lesser is the effect of collinearity. Now see what it is. What is VIF? VIF is 1 divided by 1 minus r square, which is this. Yeah, that is your that is what the VIF is. So if this one is weak, if r square is small, then 1 minus r square, this value will be high. So 1 divided by a higher value, it will be closer to 1. However, if